everyone, Matteo here from C-Tech Company down here in sunny South Florida. Today we're going to do a special project. We're going to assemble the MIT CosmicWatch. Now the CosmicWatch was developed by some graduate students at MIT a few years ago, and it has become a popular item for measuring or detecting muons, which are high energy electrons that get generated in our Earth's atmosphere when our atmosphere is bombarded by cosmic rays or other sources of radiation, including gamma rays and X-rays. So this particular kit was purchased from the UK Radio Astronomy Association, and I will put links in the description telling you where I purchased it from, the instructions, all of those sorts of things. Also in the description box you will find timestamps for the various portions of this video where we're going to go over the parts themselves, tools used to do the assembly itself sped up, and then some testing results at the very end. So let's get started. So first let's go over the actual contents of the kit. So the kit comes with some basic paperwork with links to where the instruction manual is and a parts list. And this parts list will be very useful as we check off each item one by one as we do the assembly. This primary component that I already unwrapped is are the three circuit boards. There are actually three boards here. You can see them, they're connected together. We'll do the full assembly, then we'll break them apart when we're done. So these are double-sided boards. It's a mix of surface mount as well as through-hole components, and everything is clearly labeled so you can know where each of the items are going to get soldered. Beyond this are all of the components that we have in the kit itself. We have all of the surface mount capacitors, some through-hole hardware including connectors and different sorts of things, and also the microcontroller. Talk about that more later. Here is a bag with a bunch of other semiconductor devices. And then we have all of the surface mount resistors. And what else do we have in here? We have, that's it for the components. A very key component to the CosmicWatch itself is this particular thing called the scintillator, which is basically a piece of acrylic plastic that has been designed to mate directly with one of the circuit boards, and it will screw into it. This scintillator is where the magic happens, where the muons actually produce a photon, and that photon ultimately gets detected by a device that we're going to solder here, called a silicon photomultiplier. So that's a key component. The scintillator will be mated to the silicon photomultiplier using some clear gel to make sure that there's a good optical connection, so they give you a syringe of gel in here. And then last but not least, and I purchased this separately from the UK RAA, and this is an enclosure that they had made up. So all in all, the kit and the enclosure are well worth it, since it saves you from having to go 100 different places for the different parts. So put this back in here for a second. Let's switch and talk about tools for a moment. First of all, you're going to need a good soldering iron. So here's my handy Weller soldering iron, and on it I have this ETU tip, which is a fine tip. And given what's on this board and most of the lead pitch, I think this is an appropriate tip for the job. Often I tend to use this tip, which is, if you use a Weller soldering pencil, this is the more common ETA tip, which is kind of a screwdriver tip, a little coarser than, or a little bigger than this fine tip I have here. But I believe we're going to be good with this fine tip for most of the stuff. If toward the end we have to solder some bigger through-hole components and we need a larger tip, we can always switch out. So besides the soldering iron, of course, you need some lead-free solder, and then you need some basic tools like some small needle nose, maybe some cutters, And probably most important is you need a good pair of tweezers, and maybe what this is called a pick, and we use this in electronic assembly to just move small components around with the fine touch. I also have a better pair of tweezers over here too that I might pull out if my other ones aren't quite as good. But these are usually enough to pick up the small surface mount components and hold them in place while you solder one side. And then in case you make a mistake, it's always nice to have some solder wick so you can soak up the solder and remove a component if necessary in order to do it over. And maybe a cleaning brush and some isopropyl alcohol wouldn't be bad either. Toward the end, when we're done, we'll do a cleanup of the board to remove the flux that's inside of this solder. This is rosin core solder, so it comes with flux in it, and that is all you really need, and that'll allow for good soldering joints. So let's go ahead and we'll switch the camera. I'm going to mount the camera on this arm right here so that it's projecting down on the workspace that I'm using. And also, one other thing I'll mention is it's nice to have a magnifying light like this. I use this all the time. So I'm going to use this in concert with the camera being located here to give you guys a good up close and personal view of the soldering as it's being done. Okay, so we're ready to get started on soldering here. And we're going to go ahead and follow the list that they gave us with all of the components, and you can see they did a nice job of laying everything out for you. You should always do the small, lowest profile components first, and this would consist of the surface mount resistors, all of the R devices, and then all of the surface mount capacitors, all of the C's, and then we'll get into the bigger stuff further down here. So as you can see in their bags of baggies, they conveniently mapped everything out where you can, all the resistors are in individual pouches in this one larger bag, and everything you need is in order, in the order that you're going to solder it. So I'm going to break all of this stuff open and get ready to get started here on soldering the first resistors. Okay, so the first resistors are going to be R11, 12, and 13, 49.9 ohm resistor, and these are not static sensitive, so you don't have to worry too much about that. If you are in a dry climate, once we get to some of the semiconductor devices, it's also advisable that you make sure you're grounded before you handle anything, and you can ground yourself by touching any sort of grounded appliance or anything that has a ground in the metal skin. You can just discharge yourself before you touch anything. If you do have a wristband, a static wristband that gets tied to an earth ground someplace, that's also a good idea. Here in any high humidity environment, though, we don't have to worry too much about static. So these components come in a strip that is normally fed into a surface mount pick and place machine. So you have to peel back the plastic in order to get at the resistors. So if you want to do one at a time, you can take the resistor out of this packet and grab it with your tweezers. So you can see here I have one resistor that is on my tweezers, and this is going to be placed where R11 is, which is right here. So we can put that resistor, and we're basically going to solder it between those two pads. So the way you do this soldering is, first you need to solder one side kind of roughly. So I'm going to add a little solder to the tip of my brand new soldering iron here, which I haven't really conditioned yet. So I'm going to condition it a little bit, make sure that solder is sticking, and I have a good temperature. There we go. Always make sure you clean your tip with a clean sponge. So then what we're going to do here is, while I hold this resistor with my one hand, I'm going to solder it with the other and add the little solder to that pad. So you can see all I have to do is liquefy it a little bit and then let go. Now this resistor won't move. So what this allows me to do is solder the other side, like so, where you apply heat to both the pad and the resistor's pad itself, and then bring the solder in, and then you get a nice joint like that. And then I'm going to go back to the other side and do the same thing over again so I get a nice shiny joint. If your solder connections end up being shiny, then you know you've done a good job. If they look cloudy or they're not looking like they're kind of coarse or rough, or they've look sandy, then you know you've not done a good job, and the solder joint is known as a cold solder joint. So to make sure you get nice solder joints, apply heat, bring the solder in, remove the solder, then remove the heat. That's typically the best technique, especially when it comes to surface mount. So I'm going to try to zoom in a little bit here so we can see a little bit more, maybe with a couple of these, and then I'll zoom out as we get into some of the more redundant stuff so I don't have to drag you through this. All right, so now we've got R12 next, so we'll go ahead and we'll grab a resistor out of our pack and do this again. So there's the resistor. Preferably, it's always good to put the resistor with its numerics up, so that way you know what the value of the resistor is. And then we're going to go ahead and solder it to the one side, and so it gets held in place. And once it's held in place, then I can come solder it in on the other side. Make sure that joint looks good, and then do the first joint over again, and that's good there. So that's basically what you're going to do dozens and dozens of times here as we go through this whole assembly process. So at this point, I'm going to speed things up as I blast through the resistors and the capacitors so that you don't have to wait for me. And then once we get into some of the more complicated components, we'll slow back down again. Okay, so the next component that we're going to do now that the capacitors and the resistors are done is this Ferrite bead inductor. Now, we just did L2, which is also an inductor, but it is of a package that's very similar to a surface mount resistor or capacitor. L2, however, is a little different, so I wanted to stop and talk about it a little bit. I've already taken it out of its bag, and this is a device right here. It is actually a little coil with a little ferrite core, and then two legs that may be tough to see, but they are only exposed on the bottom and not on the top. So the way you solder this is when it gets placed on its pad, you're going to basically just melt the solder on the pad and allow it to flow underneath and melt the solder on the back side of these pads that are on the inductor itself. They're tinned already with solder, so everything should work out fine as far as it's sticking and making and holding in place and getting a good electrical connection. So I've added a little more solder to this pad right here where L2 belongs, and then what we're going to do is heat that pad and liquefy it and then move the inductor into place. And then when I do that, the solder underneath the inductor will melt and everything's good. Then we're going to come into the other side and do the same thing, and you might want to be a little more liberal with the solder on this. Not too much, so it doesn't cause a short underneath. And then obviously go back and re-hit the first one just to make sure it's nice. It's not a cold joint, nice and smooth. And there you go. Okay, the next component that we're going to do are these two Schottky diodes. Now, these are the first semiconductor devices that we're putting on here. Everything else has been passive so far. And everything else has no polarity. However, diodes do in fact have polarity. On the board, you will see they have marked where the cathode goes by virtue of this line right here, which is toward the pad here. That is to your right and my left. This is the cathode, the other side is the anode. So this is the negative side of the diode and this is the positive side. So you have to make sure you place the diode in the proper polarity and orientation in order for it to do its job. Now, every diode is different, so as far as how its markings are, some might have a line, some may have a little dot. This particular one, it appears it has a line. So it's not easy to see, but in the right light, and I'm going to pick it up here and turn it around, you might be able to see that there is a line on this side of the diode and none on the other side. So the line goes with the line. That's basically all there is to it. So in this case, since there are two vias through these pads, which leaves a little hole, I'm going to add a little solder to that one pad in order to allow me to put the diode into place on one side, and then we'll hit the other side. Now, when it comes to soldering diodes, you do not want to overheat them. They have a pretty high tolerance, almost surface mount components do, but this is one of the cases where you don't want to linger for too long after you've accomplished a good solder joint. And once it's accomplished, then you can give it a second to cool and dissipate its heat back into the board while you and wait, and then once it's cooled off a little bit, then you can go back and hit the other side, and then you're done. So that's how you solder the diodes in. Make sure you observe the polarity. The line goes with the line. And after we finish this, I'm going to go ahead, since we are done with all surface mount discrete components at this point, I'm going to go ahead and give this board a good cleaning. I'm going to utilize some isopropyl alcohol and a soft brush that will allow me to clean up some of the flux that comes out of the solder itself. This is no clean flux, however, I do like to clean flux whenever possible because if it sits for a long time with flux on its connections, it will eventually cause a little bit of corrosion since flux is acidic. So we're going to go ahead and do that cleaning after this, and then when we're done, we'll come back and we're going to go ahead and finish installing the larger through-hole components. Okay, the board's cleaned up and we're ready to get started with the next batch of items. According to the parts list that I showed you earlier, which we're almost halfway through, the items they want us to move on to next do not correspond to what the instructions online tell us to do. So we're going to follow the instructions online since those are written in great detail, and as stated earlier, there's a link in the description box. So the items we're going to be working on are most of the semiconductor ICs and such. U2, U1, U6, U10, U8, which is a SD card socket, which solders similarly to an integrated circuit, and then the famed silicon photomultiplier, which is very sensitive, and this is going to be a tough solder, so we're going to take our time with that one. So I already have U2 out here, and U2 turns out to be an op-amp, nothing special from Analog Devices, but it's got a very non-standard package marking. Now, of course, integrated circuits have a pin 1, and usually their pin 1 is marked with a dot. So, for example, on the board, you can see, hopefully, there's a dot right there for where U2 is going to go. And try to get the glare out of there for you. And so this dot is where pin 1 is on this IC. Now, this IC, if you look at it, doesn't have an obvious pin 1. Usually there's a dimple in the plastic package which indicates where pin 1 is. This one does not. So I had to look it up, and it turns out, even though it's not very apparent, down one side of the chip there's a chamfer or an angle cut in the plastic. You might be able to see it on edge or just looking at it in the light. So one of the sides is completely square, and then the other side is got this chamfer. Well, it turns out this chamfer side is where pin 1 is. So if you're looking at the chamfered side, pin 1's on the left or in the corner. That would make sense for pin 1 to be in. So the orientation of the IC needs to go like this. So now that we've got that figured out, the way you want to solder one of these ICs is typically what I'll do is I'll find a pin that doesn't have a lot of traces connected to it in the corner, and convenient, since I'm right-handed, I'm going to end up holding this with my left hand. And what we'll do is I'm going to add a little solder to one of the pins that I'm going to target as my first pin to hold the chip down with. So that's going to be this one in the top left. So I'm going to add a little solder here, not too much, because we don't want it to raise the part up in the air too high. We are going to press down on it so we can make sure all the legs are coplanar once we're done getting this soldered in position. But once you've located it and over the pads evenly distributed, then you can use this one pin, pressing down on it, melting the solder, to hopefully hold it in place. Now the good news is before you solder the rest of the leads, which will commit you, because it's very hard to get these off once you've soldered them without either cutting off all the leads or using a heat removal tool, you can adjust accordingly here until you feel like you've got all of the legs landing over their respective pads. And based on what I can see here, it looks like that. So now, it does look like things are coplanar, but I'm going to do one more hit here where I push down on the IC while I'm soldering that one leg, just to make sure it's tight against the board. And don't worry about the fact that that first solder joint looks terrible. so we're going to hit it again anyway. So now we're going in and we're going to hit pins 1 through 4 on this side, one at a time. And as with every surface mount component, you put the iron on the pad and on the lead. So you equally heat the lead and the pad. And then when you see flow between the pad and the lead, you know you've got it. Same for pins 5 through 8. It doesn't take a huge amount of solder. Obviously, you have to avoid shorting the leads together. If you do, just get your solder wick out and you'll be fine. So there you go. So U2 is in place, pin 1 is where the dot is, and we're ready to go. So U1 follows this, and then U6 and U10. So I'm going to speed things up a little bit while we do this, and then we'll slow back down once we get to the SiPM module. All right, the board is cleaned up again, and we have soldered on all of the integrated circuits. The SD card socket, a little tricky. You have to solder some strain reliefs in the ends here to keep it from peeling back off the board after you solder the pins. One word of caution. On this side, when you do solder it, you have to be careful not to overheat it because you can start melting some of the plastic internally, which happened to me. But fortunately, when I tested it with an actual micro SD card, it worked fine, and all the contacts inside are making good connection and everything looks good. All right, so now we're moving on to this silicon photomultiplier, which is going to go right here on the back side of this board in the corner. And this is going to be pretty tricky because this device is very fragile and very sensitive. We have to be careful. It has polarity as well, and we also don't want to scratch it. So we're going to and we don't want to touch it with tweezers. So there's a whole lot of things here. So we're going to somehow have to get this out of here without touching it with tweezers, which I think I can do. And then try not to touch the actual active face is facing up in this package, and the leads are facing down. So this is a clean surface, so we're going to try and manipulate this perhaps with a piece of plastic here. See where it lands. Yeah, so it definitely looks like the leads are, we don't have much choice but to touch this with some tweezers, and we're going to just grab it on the edges here. So this is the active side, and I'm going to assume this is the not active side, and it isn't. So on this side you can actually see, if I can grab this from across, it won't hurt anything. You just don't want to scratch the face. Here are our leads. You can see them, they pass underneath, and the pin 1 indication is, according to the instructions, where a triple piece of tiny pads is in the corner. So here's the triple right there. You can barely see it, and I don't know how easily it's going to be visible from the top. So you can see it from the top, and that pin 1 is going to go there. So this thing's going to get lined up like that, and we're going to very carefully solder these opposite corners in place. There's only 2 connections, and one of them is going to be there, and the other one's going to be here. So we're probably going to want to just heat up as much solder as we can here and feed it in, and then do the same in this corner. Overheating this plastic module is easy to do because there's not a lot of heat sink here. So the lead itself is your only heat sink to draw heat away once things have melted. So it is going to be a trick, and hopefully there is a test to run after we're done here to make sure that it's working right. So we're going to go for it here, and I think we can wipe it off later with a soft cloth, and no worries with that. So, and I don't want to put a piece of tape on it either because we're going to end up with some adhesive. So positioning this as best as possible, using my finger and manipulating it here to get that corner to line up. That corner and that lead do not have a lot of, they're not much over the pad, but just barely. Just take your time. Make sure it's lined up. If you want to look at it under magnification, better magnification than what I have here, using an eye loop or something like that, feel free. It never hurts to inspect what you're trying to deal with here. Obviously, once we solder this down, we have to be very careful when we flip this board over, and we have to avoid scratching the surface. Any scratches might result in, photons being reflected away when they would have otherwise come in, so it might interfere a little bit with the detection. There's some tinning on this pad already, so I'm going to see if that works. I can already feel it heating. My finger will be a heat sink and also an overheat detector. Alright, so it does appear we did get some soldering in that corner. And I have to try to hit this corner. Probably should have added a little more solder to the pad before we went in. That would have helped. Okay, that should have done that one. We had some good flow underneath. Let's see if it moves. No, it's not moving. Those are golden leads, so they solder easily. There's that one. And we don't want to hit this more than once if we can avoid it. I'm hopeful. This alcohol is usually pretty friendly in terms of it's not going to attack any plastics or anything like that. So I'm going to try to clean these pieces of flux off in these corners, and then we'll get another rag that's a little less abrasive and touch up the top later. So looks pretty good. It has to be coplanar too, because the plastic scintillator that's going to squash up against this is going to be kind of probably suspended in space. We're going to screw it into place. It may have washers. I don't know what they did, but we'll see when we get to that point. Now, according to this, there is a test that we can run with a meter to verify that we have conduction in one direction and no conduction in the other direction. And I'm going to be able to get the meter into the view here, possibly. And turn it back. So we're going to, they recommend doing a continuity test instead of doing a diode test. In one direction, we should have high megohms. In the other direction, it should be totally open. It'd also be good if we can touch this from the other side. So I'm going to put down a piece of plastic here and rest it on that. And then I'm going to do this test from this side. See your capacitor's charging here, and it goes to overload. And if we flip the leads, we get some conduction. That makes more sense to me. So this is the reverse bias direction. You're charging a capacitor until the capacitor is charged and then no more current flow, so infinite resistance. And the other way, you're getting some forward conduction through the diode array. All right, so we're looking good here. This is probably what we're supposed to see. We will find out in the end. All right, moving on. All right, because of the sensitivity of the silicon photomultiplier, I've decided to cut its board away from the combination of three boards here. And I did so using some of these flush cutters. As you can see here, where the holes are, you can cut through more easily. And I smoothed the corners a little bit because we are going to ultimately have to wrap this thing in aluminum foil and electrical tape. And the scintillator itself cleaned up nicely. And what I want to do, just to get it out of the way, is we're going to jump ahead and finish this board by itself. And all that's left to do on it is to do this 6-pin connector, or header as it's called. It's the male pins, and it's a surface mount type that sits on these 6 pads. So I'd like to just get this over with so we can put this board to the side and not risk damaging it, as we still have a lot of work left to do on the other 2 boards. So this connector obviously isn't polarized, and we're going to carefully solder it. I have a rag down, a soft rag, to keep the silicon photomultiplier from getting damaged. So I'm going to add a little solder to this pin so that we can make sure that this is going to get aligned properly. Now this connector does have to mate to another connector, a female connector on the main board. And in fact, that alignment is going to be quite critical. So I'm going to add a little too much solder here, so I'm going to remove some. So we need to get this connector pretty centered. And in addition, because there are 3 things that are going to have to line up. There's going to be this male header, and then there's going to be 4, I believe 4 screws and 4 standoffs, maybe 6 here, I'm not sure in the end, that line up with the holes in the main board and sandwich this whole thing together. And we need to make sure that everything's going to align. So if we make sure we put this in the middle of all of its pads, then we will hopefully have a good result when everything has to get mated together. Try to heat up a couple here so at least it stays in place. Alright. That looks reasonable. So we'll go ahead and we'll get another pin here that should keep it from moving. All right. That looks pretty good. I'm going to do one last push down to make sure it is coplanar, and it is. And then we will finish soldering this up. All right, so everything looks pretty good here. That connector is in place. We'll do a little cleanup, and then we're going to put this board aside and move on. Okay, now that we have the scintillator board out of the way, there's still a few steps left in stage 1 to complete the job. And one of those steps involves soldering a connector onto the SD card board. And notice I decided to cut away the SD card board from the main board so that we can work with it separately now. And you know, there's the instructions. I read ahead to try to figure out where all this stuff is supposed to mount, and also how it's supposed to align with the front panel on the enclosure. And the instructions aren't crystal clear. So I decided to go ahead and see how this is going to work out, and I want to share that with you now, since there are some oddities here that don't make complete sense, but I know what they're ultimately after in the end. So there is this one bag that supposedly has a 2x4 connector in it and a 1x15, two 1x15 connectors in it. Obviously these are the 1x15, and those are meant for the Arduino Nano, which we have over here, and that'll sit on top when these go in here like this, which we can just plug in there now to demonstrate this. The Arduino Nano will sit right on top of this, and it'll stick out the front like that. And we'll solder it on this side and on this side. But we won't do that until the end. This 3-pin connector that they labeled a 2x4, it's actually a 2x3, and I read in some other instructions that I found online where I could get an overall picture of this thing. This was what came with the Nano because it's meant to go in here, and this is where you could use a different programming device to program the Atmel microcontroller that's on there versus going through the USB. So they want us to use this header here on the back side, actually going underneath the Nano, and in order to allow to connect ultimately to the SD card. Now obviously you see you really need a 2x4 instead of a 2x3, and what they recommend doing is, because not all of the pins in the Nano are getting used in the main board as indicated by these white dots here, they recommend that you cut off these last 2 pins that are over here and use them to populate 2 of these. Now it's a little crazy, and you know, there's actually another factor here involved that may complicate that further. I do actually have a 2x4 here that since I do this stuff for a living, I have some of these lying around. Actually, it was a 2x10, and I just cut it off to make a 2x4. So that'll go in here perfectly, and ultimately this is what it's going to be looking like. You're going to have the Arduino headers pointing to the top, and then this header on the bottom. Now here's where the problem comes in. If we're looking at this at an angle, we'll put the Arduino on here, and that goes here. This header, or excuse me, this SD card goes on this header a certain way to make sure that the signals line up, because if you put it on this, it'll be pinned out wrong. So it has to go with the SD card socket away from the main board in order for all the signal names to line up, which you'll see clearly written on the board, in the white silk screen, and then also on the SD card written in the white silk screen. So this has got to go on there like that. Now when you solder this in place, you'll see you've got this sandwich of the Arduino with its USB connector, and then the SD card reader with its connector. This has to actually pass out through these 2 holes. One is the USB connector for the Arduino, and then this is the SD card reader slot here, and this is for the larger BNC connection, and we have reset button, LED, stuff like that in these other holes. So if you line this up, you will see that this alignment, vertical alignment, is pretty critical, and it's unclear where it's going to fall. You have to make sure that the board is hovering above the main board and is in parallel in order to make sure that all of this stuff comes into alignment like that, if you can see it. So in any event, I'm going to go ahead and use this 4-pin header that I have in place of the 3-pin plus 2-pin, because that'll make it easier, and I may ultimately solder this into the Arduino because I do have the ability to program the Arduino a different way, and I might choose to do that down the road. But the key is that this sandwich ultimately has to line up with these holes in the enclosure, and this SD card reader is set back a little bit, but the SD card is long enough to reach in there. I already verified that. In fact, we can prove that again here if I pull it out, and you can see that it'll pass through. Let's do that. Okay, so I put a micro SD card inside of the SD card socket in order to see how this is going to look when we ultimately sandwich all this together. And as you can see, it looks like things should align reasonably well as long as I keep this SD card board parallel, and it should work reasonably well. The SD card, of course, the SD card board is going to be cantilevered, if you will, on this 8-pin header. Another reason why I want to use a solid header, because alignment's going to be tricky if we have to use one 3-pin and then cannibalize 2 pins off of those 15-pin connectors. So let's go ahead and go back to the instructions and complete what they want us to do to wrap up stage 1. Okay, so it turns out the only item left in stage 1 is to solder the 2x4 connector, which, as previously discussed, I decided to get another one instead of doing what they suggest. Solder that into this board. Now, because we're going to ultimately solder this into the main board, as previously demonstrated, I'm going to go ahead and solder the long pins into this board, into the SD card board, so that I can trim them off now. That way later, after when we're ready to do final assembly and we go in here, I don't have to worry about trimming these pins because the Arduino Nano will ride above that high enough to where they won't make any contact because of the other headers. One thing to note here is, since the SD card is going to go on in this orientation, even though the silk screen shows the connector on this side, you don't put the connector on this side. You put it from underneath. That way that you can see that the signal names line up and match one for one on the main board and on the SD card board. So let's go ahead and solder it in this way, and then we can trim it off, and that will allow us to finish this step. I'm going to use something to prop this up so that I can get a good square alignment of the pins. We'll go ahead and do one pin first, and then we'll square it up to make sure everything looks good. Alright, so that pin is soldered in, so now I'm going to hold it square and press down on it as I reheat that pin, and then I can inspect and see that things look reasonably perpendicular. So I'm going to hit another pin here, make sure we're good this way. Yep. Hit one more pin in this corner, and then after I do that, the remaining 6 pins should follow nicely. Alright, so we're looking good here. Let's go ahead and finish soldering this, and then we can trim the pins. Since these pins are all individual, they can get hot really fast, so you want to make sure you do not linger too long with your soldering so as to not melt the plastic on the other side that's keeping the pins separated, and also provides the link between, or the separation to the main board. You don't want any distortion in that. All these little tidbits I'm sharing just to help you avoid disasters. If you've done this before, then you'll know exactly what I'm talking about. Alright, so now that we've got that soldered in, it looks good. I'm going to go ahead and trim these pins off with my flush cutters, and that'll allow us to do a little bit of a cleanup, and that will complete the SD card board. So there you have it. It's ready for installation into the main board, and we can almost do that at any time, but we'll wait until the instructions say to go for it. Okay, on to stage 3. Stage 2 was the test of the silicon photo multiplier. So now we're on stage 3. The scintillator board and the SD card board are done and moved off to the side. So now, according to the instructions, we're going to, on the back side of the main board, install this 4-pin header into this location. And then everything else happens what I would consider the front side, or what they call the front side, and we have a 6-pin female socket that's going to go in here, a reset button that's going to go here, the big BNC connector is going to go here, a 3.5 millimeter power plug goes right there, a temp sensor is going to go here, and then the 15-pin 15 by 1 headers are going to go here. So I'm going to go ahead and take care of all that now and then come back when we're done. Okay, we have finished the stage 3 soldering steps, which involved soldering on this 4-pin plug for the OLED display. The BNC connector here, of course, reset button, temperature sensor, 6-pin receptacle for the scintillator board, and then this 3.5 millimeter jack, and also the 2 1x15 headers for the Arduino. I also went ahead and soldered in the SD card so we can get this over and done with. It's sandwiched in there now. The alignment with the front panel looks good, where the SD card will pass through this hole and the USB for the Arduino will pass through that. I checked that as well. So all is looking good. We've cleaned up. So what's left to do as far as soldering is concerned is we're going to solder in the Arduino when we're done programming it here. And then there's also an LED that comes off the back. And if you did purchase the enclosure kit from the UK Radio Astronomy Association, you will get a little LED holder here that requires that you pass the LED's leads through it first before you solder it in, so that way you can put this through the front panel and have it look nice passing through the front panel. The back plate has a passageway for the OLED display and also for this LED. So we're going to do that later, but first, according to the instructions, we need to move on to what they refer to as stage 4, which is the Arduino programming. So we're going to go ahead and work on that now. I'm going to try to capture some screenshots of that on the computer since it involves using the Arduino IDE and loading software. So basically all we have to do for the Arduino here is to begin working on it is to get a USB mini, not micro plug, and put it in here, and this will allow us, the USB will not only power it, but then all of the communication that is needed will also be taken care of. And if you have not yet installed the Arduino IDE development tool, you need to do that first. Make sure it has all the drivers necessary to support this particular USB adapter chip, and everything should be good to go. So let's transition to that now.
Okay, here we are ready to work on programming our Arduino Nano in stage 4 of the instruction sheet. So first and foremost, as listed here, if you do not already have the Arduino IDE installed on your PC, then you can go to this website and install it. At this website, you can see that there is the latest version is 2.0.4. That is a recent release, and that does not match what I currently have loaded on my computer, which is the legacy version. The last of the legacy versions, 1.8.19. If you have this version or you want to put the new version on, that's up to you. I did try the new version and it looks a lot different, so I'm going to leave that behind for now and stick with what I have installed and use this for the demonstration. Either will work for what we're doing, so we'll leave it up to you. The new version looks nice, but I'm not going to spend time on that right now. Beyond Arduino, we have to load these libraries in the Arduino, but we're going to come back to that in a second. So the second thing you need to download is the actual package, which does include the code and a lot of other information about the CosmicWatch, including the schematics and layout files, what have you. So if you go to this GitHub site, you will be able to find the software. And here it is here, and then in this green button there's a download zip. And once you've downloaded this zip, it will expand to look like this. So here is the zip from the UK RAA, and it all expands out like this. And within the zip, the code itself is under the Arduino, and there are 3 code files naming OLED and SDCard. We're going to talk about those in a minute here, but let's go back to one other item in the instructions, and that is the skipping step 7. Since we'll come back to that, we have to load the driver so that your computer can talk to the Arduino Nano over USB. And the particular Arduino Nano with this kit, this CosmicWatch kit, comes from a manufacturer named Elegoo, and it utilizes the CH340 chip, which is a USB to serial converter chip. That the manufacturer for that chip is WCH, and I decided instead of going to this website to find the driver, I just went to the chip's manufacturer's website and found it there. So this is what was written on the chip, WCH, and I was able to find them, and I found the driver package for the CH340 series, which covers all these parts, and I downloaded this zip. And once I had that zip downloaded, it looked like oh no, that's not where we want to go. It looked like this. So the zip expanded consisted of all of these files. And if you have a Mac computer, there is a driver package that does come with the GitHub zip file. That's right here. But the one I added, I stuck in next to it. And all I ended up doing was running the setup program, and it said, do you want to install the driver for CH340? I said yes, and it was done. So the advantage of doing that is now you have the driver set up before you plug in the Nano for the first time, so it ends up in the right place. So at this point, going back to the instructions, we can now move on and start to use the Nano. So first thing to do is let's actually plug in the Nano to make sure that it is working and recognized by your system. And I do have the Nano plugged in over here, and I have it on a live camera feed, and it's plugged in, and the power light is illuminated. And if I go to my device manager, you will see, if you expand out the COM ports, that the CH340 serial device is showing up at COM4. That'll become important when you go to configure the Arduino IDE setup once you've opened your first file and you want to write it into the Nano. So we're connected, we're communicating on COM4. So let's go ahead and open up the Arduino IDE software. Okay, we have gone ahead and launched the Arduino IDE program, and you can see it right here. And what we need to do next is, according to step 5, we need to make sure that these libraries are loaded. So the way you do that is you go to the Sketch pull-down menu and you click Include Library, then Manage Libraries. And this is going to open up a window that is going to show you what libraries you already have installed, along with ones that you can download from the web. And once the window loads, we can go ahead and type into this search box the name of the library that we want to go after first. And I did find it is case sensitive, so we'll search for the SSD 1306 library. And once that comes up, we should be able to see it here in the search results, and there you have it. Now you'll notice over here in the instructions the version that's called out is 1.1.2, but the first version offered over here in the search is 2.5.7. I have found that newer Arduino libraries are not necessarily backward compatible. So in order to avoid any issues like that, let's just go ahead and install the version that the instructions call out. And the way to do that is you click on this down arrow here, and you can scroll down and pick the particular version that you're after. And it should be right there. And once you've done that, click Install. And once the installation is completed, you should have a verification message that it did get installed. So let's go ahead then and move on to the next library, which is the GFX library. And once that is found, we can see it here. And according to the instructions, it is version 1.0.2 that we want. So let's go here and find that and install that. And we got the verification. It is done. And then we want timer 1 for the next library, and the version is going to be 1.1.0. And you'll notice over here that there is no version option to choose from, so that probably means there's only one version. So when we go ahead and install it, sure enough, 1.1.0 got installed. Now you're going to likely have to install the rest of these libraries if this is the first time you're running the Arduino IDE. I have these libraries already installed because I use the Arduino IDE for other project work for my business. So I know I already have these libraries installed. They may be of newer versions, but since these are standard libraries, there's likely not going to be any compatibility issues. So we can go ahead and close out this library manager window since we're done with that step. So now we need to go and actually get the code, open the code that the UKRAA GitHub repository download provided for us, and it was a zip file that we grabbed and expanded, and it looks like this. And in the Arduino subfolder you will find the code under 3 folders: naming, OLED, and SDCard. And the actual source code file is a .ino type. That is the Arduino file extension for a sketch or source code. And in this README you will see a description or an explanation of what each of the 3 files do. The naming.ino is a one-time execution only that simply writes the name of the detector into EEPROM, and you can make it anything you want. And then we are immediately going to overwrite this program with one of 2 operational programs, either OLED.ino or SDCard.ino. OLED.ino does the detections and writes the live results to the OLED screen, whereas SDCard does the same thing but writes the results to the SD card. And as you can see noted down here, they indicate that both cannot be done at the same time due to limited resources in the Arduino Nano. I'm not quite sure I believe that, so I may take on a future project where I try to revise the code so that both features can be accomplished at the same time. But let's not worry about that now and plan on installing OLED.ino after we execute naming.ino. So let's go ahead and grab naming.ino by double clicking on it, and you'll notice it will open up a new Arduino window. And once that window opens, we can close this empty sketch and bring this window up over here and make it a little bigger so we can look at it. And we're going to go ahead and make a modification to the naming.ino as described here in step 7, where they said change the name of the detector to whatever you want. So the detector's name is in this line right here at the top of the program, and the default name they provided was Leonardo. I changed it to be my company name, which is CTEC, and then that's all you have to do. And at this point you can compile the program by clicking this verify check button at the top, and if everything works properly you will see just a couple messages down at the bottom here in white indicating the size of the program and the resources used. If there were any errors, it would show up in red. So next we are ready now to upload the program to the Arduino Nano, which is sitting at the end of our USB cable right now. But before we do that, we have to make sure that the Arduino IDE is communicating properly with COM4, and the way we do that is by going to the Tools menu, and first you go down and you make sure you've got the right board type chosen, and in this case it is an Arduino AVR board, and the one we're after is the Arduino Nano. If you do not have this board option menu available, you might have to download it using the boards manager. It was already there, and I believe it is a default in Arduino, but I'm not 100% sure. So after choosing Arduino Nano, the rest of these items get auto-populated, and the only one you need to verify or change is this COM port, and if you did have any other COM ports, those may have been chosen by default. Obviously we want COM4, it's chosen here, so we're good there. And once you've got the COM port selected, you can now open the serial monitor window, which you want to do. And what the serial monitor is, it's a screen that's going to display any information written by the Arduino Nano as a result of its executing the program you're going to install, and it'll show up here. So this is kind of like debug or live data information. And in order for this window to work properly, you have to set its baud rate correctly, and the baud rate is not listed in any of the documentation, but I did find it down here in the program, and it is 9600 baud. So in the COM port window, or the serial monitor window, if it's not already chosen, choose 9600 baud and everything should be good to go. So now we are ready to actually go ahead and do the upload, and we do that by clicking the upload button here, which is this right arrow. The Arduino IDE will do another compilation and then immediately follow that with the actual upload to the Arduino IDE. And if everything works properly, you will get messages coming out on the COM port screen here indicating that the program ran. And lo and behold, we do. So the first message coming from the naming.ino program that runs once and then just stops is it's writing the name of the detector to the EEROM, and then it verifies it back again. So that's all that naming does. So we're done with naming. We can close it out. And now we can go ahead and open the OLED.ino program, and this will open a new Arduino window, and we can reopen our serial monitor, which is still going to be communicating the results from the previous program. Here, the OLED program, we don't have to modify anything, but as you can see, there are all the libraries in here that we had just installed. So let's go ahead and compile it and make sure it works, and that'll prove to us if our libraries got installed correctly. And it's a little bit of a bigger program, so it takes a little while longer, takes up some more space, and all looks good. So we are ready to write this to the Arduino, so we'll click the upload, and once we do that, we should get the results in the COM port screen here after the program is loaded. So take a little while. Once it's running, we get messages. So here we are. We get a from the OLED program, we get a little introductory title block here indicating this is the CosmicWatch, and the name of the detector is right here. Now, if once the CosmicWatch is fully assembled, if you do connect the USB cable, you will get live data here for every detection, similar to the data that gets displayed on the OLED screen. So that's useful if you want to monitor what the CosmicWatch is doing from your computer, in addition to watching the LED and the OLED screen on the device itself. So we are done with installing the Arduino programming, and we are ready to go ahead and complete the final assembly of the hardware. So let's close this out and move on to that now.
Okay, we've got our Arduino Nano programmed, and we're homing in on the final steps here. We're in stage 5 of the instructions, where we're going to finish installing the remaining through-hole components into our main board, which, as we last left it, is still in this configuration. So what's left to do is solder in the Arduino Nano and also this LED, which goes in this corner over here. If you did purchase the enclosure kit, the LED, it does come with an LED holder, which has this little rubber grommet that the LED has to get thread through first before you solder it into the board, so that it'll plug into the back of this once it's mounted on the wall of the enclosure over here. So we're going to do that step first, and then we're going to solder in the Nano. One of the wish items that I had was I wanted to install this unused 2x3 connector into this location here for programming, but as it turns out, it does interfere once soldered into this position. That connector will interfere with the scintillator board, which gets plugged in here into that connector. It will interfere with it and potentially contact some of these components. So unfortunately, I'm not going to be able to do that, but I'm glad I checked up front. So let's go ahead and forge ahead and do the LED installation first here. Okay, the longer of the two LED leads is the positive. So we're going to, or the anode, as it is called. And per the instructions, we're going to leave all the length. So we're going to put this in square. The positive lead is longer than the negative lead. So we're going to prop this up in a way where we can position this LED such that we get maximum length, which is going to be set by the length of that negative lead. And we're going to go ahead and solder this into place, readjust it to be square, and then we'll be ready to move on. Okay, the LED is in place. Let's go ahead and permanently install our Arduino Nano. Make sure it stays square. Alright, now that the Arduino board is soldered into place, we're going to do a little cleanup here using the technique I mentioned earlier, which is basically one of these flux or acid brushes and a paper towel where you can kind of do this over the top of the connections just to remove the bulk of that flux. And this way it's not dousing anything to any great extent, and you can use your finger as well to kind of run across and maybe pick up a little bit of as much of that flux as possible. It's, once again, it's no clean flux, so it's not critical that we remove it all, but it looks a lot nicer and less chance of corrosion over time if you clean off a good portion of that flux. And alcohol, of course, is volatile, so it dries fast. However, it is conductive. So if you do a cleaning here, it's best to make sure everything's dried before you go ahead and energize anything. So we're now at a point where we have completed the soldering on this section of this part of the main board, and all that's left to do is the testing step and then final assembly. Okay, we're into stage 6 of the testing now. We have the fully assembled and cleaned up CosmicWatch board, and I've also broken out the OLED here, which comes in a nifty little box that will then plug into the front on its 4-pin connector. And the first thing they want us to do is plug in the USB cable again in order to provide power and make sure that the LED flashes. So after we plug it in, boom, we see a flash of the LED. So that means we're looking good there. The next step is they want us to unplug power, go ahead, plug in the OLED, which goes into the front here, like so. And now we can go ahead and plug it in again. And when we do that, I can do this so that you can see it, we should get some stuff on the screen. And indeed we do. In fact, it's displaying some information and it's counting. Of course, the scintillator is not plugged in, so it may be reading some noise. That's fine. And the display appears to be working. And they said hit the reset button and make sure that it starts over again. And it does. And all is looking good. So we're looking like we passed the smoke test here. Very good. So while everything's powered up here, they also want us to test one more thing. If you see on the board here where the scintillator board is going to plug in, there is basically three signals, a high voltage, ground, and a signal, and each of these pins are doubled up. So they want us to measure the voltage, the DC voltage between high voltage and ground to make sure that the 29.5 volt boosting power supply is working before we subject the scintillator and the silicon photomultiplier to that. So if I go between here and here, we do in fact see that we've got 29.45 volts, which is pretty much right on the money. So that means we have good power that will go to the silicon photomultiplier, and all should work well. So that concludes the testing done in stage 6. Okay, we're now at the point where stage 7, and we're going to do the assembly of the scintillator module. So I've broken out the necessary parts for that, besides the scintillator itself, which has been sitting off to the side. We have the plastic scintillator itself, a gel syringe, which is going to be used to make a good optical connection between the acrylic plastic and the silicon photomultiplier. A couple standoff screws that hold the standoffs into the board and also the main board, and then 4 screws to hold the plastic scintillator onto the module. So first step is to install the standoffs into the scintillator module. So we're going to use 2 of these screws that are here. They're a little shorter, the standoff screws. And we're going to save 2 for later when we attach it to the main board. That'll be done after we're done with the assembly. In this section 2 is where we get to wrap the scintillator module in order to make it reflective and also light tight. And we're going to watch a video. Before doing that, there is a video suggested in the instructions that gives you a guide on how to do that. So without touching anything or touching the silicon photomultiplier, we're going to install these 2 standoffs into the 2 holes that have a countersink drilled into them. Hopefully the screws lock in nicely and we can do this by hand. If not, you can grab the standoff with some pliers, and then looks like it is one of those Phillips heads that's requires a special bit. But I believe if we go large enough here, we're going to be okay. So make sure it's tight. Okay, so that completes that step. Okay, we're at a point now where we need to first wrap the scintillator plastic in some aluminum foil and prepare that to then mount the scintillator module to it using the optical grease. So there's a video in the instruction sheet that they referenced that you should go watch, and I did watch it, and I took away from it a few things. First of all, the size of the aluminum foil, which they didn't specify, make a square that's 4.5 by 4.5. Excuse me, 4.25 by 4.25. And you want to put the shiny side of your aluminum foil in. So you can see here that we're a 4.25 and it's a square. Then you cut out the corners kind of in this cross type fashion where when you go to wrap it, there's some overlap here. And you'll notice that the wrap does not quite cover the whole thing. And the reason is you want the foil can come up to, this is going to mount like this, the foil can come up to but not touch the scintillator, the silicon photomultiplier's legs. This is a ground connection as these are, so ground is fine, but not the legs. So we have to make sure the foil doesn't quite come up far enough, and we have to make sure it's centered. That's probably the most, you should take, difficult part to prepare. Second is I would recommend using quality electrical tape. You know how electrical tape can deteriorate and get gooey over time. So you're best to just go for the 3M Scotch brand tape that you can get at any local hardware store. It's worth the investment. I use it all the time for everything that needs electrical tape. So at this point, what you're going to do is cut a couple strips, cut a strip of electrical tape that'll go around the whole thing, and then we're going to cut it in half. So we're going to have a half strip. So we can go ahead and do that and have that prepared, and then it'll allow you to actually do the wrap. Okay, so we have the tape prepared, and we're going to go ahead and do this wrap. Trying not to crinkle the foil and keep it as tight and as smooth as possible. Basically what you're doing here is you're making a reflective container, so any photon that gets generated inside of the scintillator plastic will bounce around until it finds its end. It's the end of its life when it lands on the silicon photomultiplier. That is the magic behind how a muon creates a photon, and the photon in turn gets detected. So my half strips of tape are here, and I'm going to apply them roughly in this spot so that, and as you can see, the foil did crinkle. It's not what I wanted it to do. Not sure why that happened. Probably because I stretched the tape. So let's try that again. See if we can do a better job. I won't stretch the tape this time. That seems to be doing better. And voila, that actually worked pretty decent. So next, we'll do this side, pulling it as tight as we can. Well, pulling it as tight as we need to in order to keep everything smooth. And there you have it. Now, we look reasonably well centered here. Let's hope that we are. We're going to have to make sure that that scintillator doesn't touch this piece of foil over here, and I think we're okay. It's going to be close. We might have shifted this a little bit. Not sure if I can spin it at all. Don't believe I can. You don't want to be careful with trimming at this point because you don't want to scratch the plastic if that can be avoided. So let's go ahead and punch some holes in order to know where the screws are going to fall, make it a little bit easier. If you press down, you should be able to find the hole locations. And if not, then you might have to hunt a different way. And once you find one, it'll help guide you for the other ones. They become visible when you do press down. So now we have a guide to see if we have encroached upon the scintillator too much with that one edge, and it looks like we should be okay. we have adequate clearance. So at this point, what you do now is we have to apply some of the optical gel that they provide in a syringe, and they want you to use no more than a 3 millimeter blob on the silicon photomultiplier itself. So you can take your blob after you make sure things are reasonably clean, put it on there. It's going to ooze around the edges a little bit. That's okay. Obviously, it's not conductive, and you just want to make sure you don't leave a big mess. So once that's set up, now you can lower this into place, aligning the screw holes as best as you can. It's symmetric, so it can go in any direction. And then you get your screws, the 4 scintillator screws, and put these in. Now, the board is going to be suspended up off of this plastic by the thickness of the silicon photomultiplier, which is maybe a couple millimeters, not even, maybe a millimeter thick. So we don't want to over tighten these screws. We have to carefully install them and balance the force in all 4 corners such that it is held snugly against the plastic, but not unduly crushing and bowing the board. That could break the solder connections on the silicon photomultiplier, which we're tough enough as it is. So now you can see the screws are countersink type screws, but the holes are not. So the screw head is going to stay above the board a little bit once it's against. So don't expect that to go down flush. So now that they have all met, you can do kind of 4 corners, and this is definitely finger tight. It is plastic, not a lot of vibration going on. You could strip it, obviously, if you get too tight. Since it is plastic and there's not a lot of vibration, I don't suspect these screws are going to walk back out. So once you feel like you've got a good uniform press, you can call it done, do a little inspection from the side, kind of make sure your gap is uniform all the way around. Careful with your foil, don't want to cut it or leave any light gaps here. You can avoid it. Any light gaps will just be lost reflections. We're going to now tape this up entirely in order to make it light tight. So now we're going to apply full pieces of electrical tape wrapping everything, and all we're going to leave exposed are these standoffs and this 6-pin plug. So I'm going to do that, and then we'll come back and do the final assembly. Okay, so we have the scintillator attached and taped up and light tight, and in fact Now that it is light tight, the original test that they asked us to do where we did an ohms reading from one side versus the other is now it does what it's supposed to do. You can see that we get some conduction in the megohm range in one direction, and then in the other direction it goes to overload as soon as the capacitors charge up. I also found that if you use the diode test, you can also verify good connectivity here too, because one direction it won't conduct, in the other direction the diodes should conduct at about a 0.6 volt rate. So this thing is looking pretty good. So let's go ahead and hook things up and see if we get some favorable results. So at this point we have the main board here and everything's in. LED is not dressed yet, but that's okay. We'll do that when we go in the enclosure. So obviously there's only one way this will fit in. You plug that in there, and then we can plug in some power. And hopefully we're getting a few counts here. That's encouraging. LED is picking it up. I'm not sure if it was my light or anything like that. The rate seems pretty high, about 4 counts per second, which is a little higher than they suggest for the background. The background is supposed to be about 1.5. Perhaps there is a lot of cosmic radiation right now. There might in fact be, because there was supposed to be a solar storm hitting today, which is the 21st of March 2023. So it's possible this could be real. So anyhow, we'll go ahead and finish the final assembly and go from there. Okay, for the first part of our final assembly, we definitely need to affix the scintillator assembly to the main board, and the way we do that is use the last 2 screws that were labeled standoff screws, and those are going to be put in from the back here. These are going into metal standoffs, so they're pretty durable, although no need to over tighten anything since this isn't a structure that's going to withstand a lot of physical stress. Okay, so once that's done, we have basically the whole thing and it's ready to go in its enclosure. Now the OLED does have a sticker on it that we can leave on to protect that for now. And bringing out the components to the enclosure, we have this clamshell, which is going to be the primary part of the enclosure. And then we've got the front and the back covers, and they give you some feet and some screws to hold everything together. A serial number sticker, which we don't have to apply, and then there's also a decal, which you could put on the top here if you'd like. So the way this enclosure works, and I've experimented with this a little bit, is it goes into the second shelf, and you basically line it up like this. And one of the things that I've noticed is it doesn't slide in easily because the clamshell is a little bit compressed, so you actually have to pull on it, and as you pull on it, it'll slide in. So you have to separate the clam a little bit, which is tougher to do now that the board is fully assembled. You definitely don't want to force it. And then it has to get put in such that it's even. And typically what you're going to probably end up with is the OLED a little bit recessed, but up against the plate, kind of like that. And then the LED, of course, now you can dress it a little bit more. And ultimately, we're going to attach our piece here to the housing in order to finish that off. So probably going to end up splitting the difference here. Everything's going to line up nicely here, as you can see. So we should be good to go. So I'm going to go ahead and complete that, not make you wait through that, and then I'll show you the finished product when we're done. Okay, there you have it. The UKRAA CosmicWatch, developed by MIT, fully assembled. And if you plug it in again, you'll see that it comes to life. And it is still continuing to read a rate of around 4 hits per second, even though it's in its enclosure now, so we're pretty certain it's not a light leak. And must be something going on. Either there's a particle generator in my workplace here, or there's something going on in the upper atmosphere thanks to some cosmic radiation, or maybe a solar storm of some sort. Or there's a gamma radiation source nearby that I better go and find, right? So anyhow, yeah, everything's looking good here. We've got our BNC output here if you want to hook it to an oscilloscope, reset button, the phone jack for if you want to link two Cosmic Watches together in a companion mode. And then of course you've got the SDCard slot and the USB connection here. So looking good, and we are completed with this project. So like I said, check out everything in the description box below as far as links of where to purchase one of these kits. You can even purchase them fully assembled if you don't want to go through what I just showed you. And you should be good to go from here. Feel free to reach out and put any questions in the comments below. Thanks for watching.